All right, everybody, here is a quick video, maybe not so quick, for Unit 8 on mechanical waves. I had a lot of people request that I put up a video, so my plan is to sort of talk through most of the notes from the unit. Again, probably not do too many sample problems. There are some sample problems that were in the notes that I'll kind of talk through. A lot of the work is already done out, so I'm not going to do those again, but I'm going to sort of dwell on and try to hit many of the bigger topics that show up in the actual test. I've got the test right here in front of me. So first off, just the idea of waves as being traveling disturbances that carry energy from place to place. In our case, we are talking about mechanical waves, particularly mostly sound waves and waves that are on strings. We really didn't talk about earthquake or water waves, but the same rules apply to those that apply to our sound and string waves. And the big thing here is that this word mechanical means that there has to be something that is moving. In order for these waves to travel, they have to have a medium, something that the wave actually travels through. So for sound waves, that's typically air. Most of the time, sound waves are traveling through air, especially when they reach us. Water waves, we got to have water. Earthquake, the earth has to be there for the earthquake to happen. If there's no earth, then there's nothing to vibrate, and same with strings. That is not true for non-mechanical or electromagnetic waves, and if you're more interested in those, take AP Physics 2 next year. But we had two sort of flavors of waves, two types of waves. The first, transverse waves. They are waves that move the particles in a perpendicular fashion to the direction of the wave. So the wave, as you can kind of see up here, is moving to the right or to the left, but a particular particle on that wave is moving up and down. Just remember that as a particle moves through, a wave moves through a particle on, say, a string maybe, it goes through 4 amplitudes. This particle will go up to the top, back down to the middle. It will go down and back to the middle. Think of yourself at a sort of like a wave pool at, someone today was saying, Oceans of Fun or whatever it is at Worlds of Fun. If you got the wave pool, as the waves come to you, first you go up, so you go up an amplitude, you go back down to sort of where you started, but then it dips down. The wave has a trough to it as well, so you actually fall to a lower position than had there been no wave, and then you come back to that initial equilibrium position as well. So in any single period, any single wave that goes through a particle, it goes through 4 amplitudes that particle moves through in that period of time. Wavelength is just from peak to peak, or from trough to trough, or from equilibrium to second equilibrium. Those are all examples of what the wavelength is. We have crests and troughs, peaks and troughs a lot of times I say. And then an amplitude of a wave is one, the distance from that equilibrium, from that middle position, up to the crest or down to the trough. It is not this entire piece. That is not the wavelength. I'm sorry, that's not the amplitude. The amplitude is just half of that. It's either from the middle to the top or from the middle to the bottom. The biggest equation we have for this unit is the velocity is equal to the wavelength times the frequency. So that equation is definitely a must, I would say, for the test, being able to use that. And again, that is the velocity of the wave, how fast the wave is moving side wave. It's the wavelength times the frequency. So realize that if you do something to one of these, right? If I double the wavelength, my frequency has to get cut in half if I'm going to keep the same velocity. And the only ways that I can really change velocity, we'll get to in a little bit, but if I'm on a string, there are certain ways I can change velocity. If it's air, really the only way I can change velocity is with a different temperature with that equation. So if neither of those things change, then this has to be true, that if you do something to the wavelength, you have to do the reciprocal to the frequency and vice versa. That velocity is in meters per second, wavelength's got to be in meters, and frequency is in hertz. Remember, that's per second, and you can go between period and frequency, with period is 1 over the frequency, be able to switch back and forth between those, both be able to get the period off of a graph as well as calculating it. And if we're talking about the average speed of a particle, that is 4 times the amplitude. Remember we said about a minute ago that the amplitude is 4 times the amplitude is the distance that a particle goes in one full cycle, one full period, and the amount of time that takes is the period. So the speed is the distance over time. So 4a over the period. And the energy of a wave is dependent on the amplitude. The more energy it has, the more amplitude it has. Secondly, we have longitudinal waves. These are our sound waves. They are compressional waves. When a sound wave hits, it can only push back and forth on other particles. It cannot move other particles side to side. So if you're looking for a longitudinal wave, that is one where you're sort of pushing on those particles, but a transverse wave, one of the other ones, is one where you're actually pulling it side to side or up and down. The longitudinal is just pushing and pulling, but the same rules apply. The velocity of the wave is still the wavelength times frequency. Speed is still distance times time. Instead of calling them peaks and troughs, we call them compressions and rarefactions, and we treat them very similarly to the other waves. A couple things here with waves on a string. Let's see if we can go to some of these. Pull those up, see what those are. Activate Java. It's not working. Oh well. Maybe go and try some of those. It gets you sort of a look at how the waves work. If you move up and cause an oscillation, you can change the amplitude, change the frequency. It's very slow. But you can get these waves tap, and we'll see more of that here in a minute. Just to sort of go through some of that same stuff, following waves is not mechanical waves. That would be radio waves, because those are light waves. They are electromagnetic spectrum waves. That's the only one that's not. The rest are. Sound waves have compressions and rarefactions. They are longitudinal. For mechanical waves, the energy is associated with amplitude. A transverse wave, the frequency, here we've got the calculation there. The speed, it tells us, is 24. The wavelength was 0.46, so you divide over and you get 52.2. And for B, we're looking at speed as distance over time now, because we're talking about how long it takes to get from one end to the other. Still the same speed, but now the distance is 0.78 instead of the 0.46. Math it around, and 0.78 divided by 24 is that amount of time. It's relatively short. So a little bit about sound waves. The lower the frequency, the lower pitch, higher frequency, higher pitch. So if we have a long wavelength that is a low frequency, longer wavelengths result in lower pitches. Range of human hearing, 20 to 20,000. Below that is infrasonic. Above that is ultrasonic. And this equation is the speed of sound through air. It's only through air that this works with. If you've got something else, there needs to be some other equation that would be given to you to calculate it. But 331 plus 0.6 T, that T has to be in Celsius. So with that, we have that equation being given to you on the test. You don't have to memorize that. It will be given to you. Speed of sound at 20 degrees Celsius, plug in the 20 for this T, that gets you 12 here, and 343 is the correct answer for there. That's sort of room temperature speed of sound, is 343 meters per second. With that, we can use speed equals distance over time, and the most common way we use that was with an echo problem. The big thing here is we've got our speed of sound given to us. It might give us the temperature instead if we're going through air. But when we send out a pulse and we hear the echo again after some period of time, remember that that is the time that it takes to go twice the distance you are talking about. If you have an echo, it goes sort of one direction, and then it goes back. If it tells you, how deep is the water, how far away a wall is, that is only half of the distance that the sound traveled, which means you either need to use half of the time or do this and then take the final answer, that distance, and divide it by 2. So if you have the speed, you multiply it by the amount of time, that gets you the distance that the sound actually traveled, but you are only worried about half of that distance. If you are talking about how deep the water is or how far away a wall is. That's from last unit. You don't need that. But one of the ways we did these echo problems was with a graph of an echo. A couple things to be careful of here. Make sure that whatever point you are measuring from is a point that is constant for each of the echoes that you pick. So if you're going to use the beginning of the sort of sound burst, make sure that you use the beginning at the next sound that you hear. So here's the initial sound, and here's an echo, and here's an echo, and here is an echo as well. So we only need one echo to do this problem. So if we are given the amount of time, the problem might tell us either the length of the tube here, or it might tell us the speed of sound and ask us to find that distance instead. Just remember that when you're doing these as well, same as the other one, if you are given a length of tube, let's say it was 1.2 meters was the length of the the distance to where the echo hit and then returns. This time is twice that distance, so that's why here we've got the 2.4 with that time difference there. A couple other things here. Just remember, frequency is number of cycles per second as opposed to seconds per cycle, which is the period. When we talk about loudness, this is where we get into decibels. We start talking about our logarithms. Even though sound waves are not transverse, we still represent them as transverse waves because they're easier to draw. They're less of a pain. It depends on the amplitude. Our sound depends on the amount of energy. That being said, we don't perceive it as a linear scale. We perceive it as a logarithmic scale. Twice the energy doesn't mean twice as loud. So if you get a problem that's like it doubled the energy, it didn't get twice as loud. The decibels didn't get doubled. Here's some decibel scales. If you're interested, you can look through those. But what we're really worried about is the decibel level of sound equation. Again, this will be given to you as well. I'll make a little edit here. Instead of saying decibel level of sound, that beta really represents the change in decibels. So if you have two sounds and you plug each of their intensities in here, you get the change in decibels. So let's say I had one intensity that was 5,000 and the next was 7,000. I would plug in 5,000 for this I and 7,000 for this O. It would tell me the difference in decibels between the 5,000 and the 7,000. I would get a negative number because the 5,000 is less than the 7,000. We actually have less decibels on that one. If we flip-flop it, then we just get the same number, but positive. When we talk about intensity of sound, our unit is watts per meter squared. It's not super important for us, but this number here is the threshold of human hearing. So if a problem represents as the threshold of human hearing, that just means that one of these values, probably the bottom one, has to be this number. And that when that happens, your change in decibels is your decibels on what we consider the normal decibel scale. We set that threshold as a 0 value, the hearing threshold. That sound intensity is 0, so we work up from there. So there's a little sample problem here with it. Remember, when you're trying to get rid of the log, you have to take 10 to whatever this is equals the inside stuff. A little bit of algebra there. But there are two other ways we can do these problems. The first is if I give you, there's another sample problem. If I give you 2 decibel values and then ask you for the, how many more times intense is this sound versus that sound. So let's say, 76 and 56, the change in decibels is 20. And then I've got 10 times the log of everything that I'm looking for. Divide by 10 gets you 2. And then it is 10 to the second power equals the stuff inside, the stuff that you're looking for. So if a problem asks, you know, what is the difference in intensity, that is what you're doing. The other way to do it, I'll kind of slide one in here, is if I told you, you know, one is 170 times the intensity. Let me actually walk over to the whiteboard so I can write instead of trying to click right. So if I said one sound is 170 times the intensity, in that case, you know, and then I'm looking for what is the difference in decibels. So the difference in decibels is that beta. I'm looking for it. That's equal to 10 times the log of the difference in intensity. So let's say I had sound A and sound B. Well, I'm saying that sound A is equal to 17 sound Bs, you know, and sound B is whatever it is. So if I plug those in, those intensities here, I've got 17 times the intensity of B over just the intensity of B. I've got A, which is equal to this, over B. So those B's cancel out. So really, I end up with just 10 times the log of 17. So when you have one of these problems, I'm sorry, not 17, 170, said from up above. So when you have one of these problems that says the intensity is this many times, really you can just plug that into that parentheses by itself. Everything else will kind of take care of itself. And remember, that's the change in the decibels. So if you do that, it comes out to about 27 probably. I got a calculator here. So 170, take the log of that and multiply it by 10. And it's actually 22.3. So that, remember, is my change in decibels. So if the problem said the initial sound A is, let's say the, you know, sound A has a decibel reading of 45 decibels. This means that A is 22.3 times louder than, I'm sorry, 22.3 decibels louder than B. So if I want to know what the decibels of B is, I would take 45 and I would subtract that 22.3. Because what this says really is 22.3 equals A minus B. It equals whatever's on top minus whatever's on bottom as far as we're, you know, our loudness scale. So be able to do all of those problems, whether it's using the threshold of human hearing in there, or a problem where I give you 2 decibels and ask you for the sort of the factor that the intensity changes, or if I give you the difference in intensity, be able to find the difference in the decibels. Little sample problems here and there. And then we've got the Doppler effect. And the Doppler effect basically says that if we've got a moving source of sound, if a source of sound moves, then whichever direction it is moving is going to experience a raised frequency of whatever sound it's producing. So if we got this little guy and we say that the speed of the source is 0, if he's just not moving, he produces these sound waves, and they're all anywhere around this little source of sound is going to be the same frequency. If you put your little mouse there, you know, it hits. But up here, if I go over here, it's the exact same. It hit. When I start actually moving my source, if he's moving, on one side we get these compressed, we get a very much higher frequency of sound waves in the same direction that he is moving. But on the back side, we get a much lower. This is the same reason that as a cop car goes by you, you hear the siren very high pitched as it's approaching you, and then when it passes, all of a sudden it drops off to a much lower pitch. Couple particular situations: if we move at the exact same as the speed of sound, the speed of the wave, speed of sound is the same as the speed of the source. We call this Mach 1. We get this situation where we layer all of those sound waves on top of each other. We get what's called a sonic boom. So recognize that if this is the case, your object is moving at the same speed as the speed of sound. And then one last one, if we move faster than the speed of sound, we get this nice sort of wake pattern, as if you were moving on a jet ski. This is the reason why that forms behind a motorboat or a jet ski, is because the boat is actually moving faster than the waves it is producing. So big thing with the Doppler effect is be able to tell sort of from one of those diagrams, you know, which way is your object moving? Is it moving faster than, slower than, equal to the speed of sound? And sort of which direction is going to have higher pitch, lower pitch, the same pitch as it goes with the Doppler effect. And then we started talking about resonance, and we got into waves on a string. Resonance just means that we can form what are called standing waves. This stuff is not as important, but the idea of the natural frequency, we have to be able to fit those waves onto a string or into a tube. Constructive interference, destructive interference, know the difference. If our peaks line up and our troughs line up, that is constructive. We add those together. If we have destructive, that is where we have a peak and a trough together, a crest and a trough together, and then they cancel out, assuming that they are the same amplitude. We'll talk about that again once we get sort of down the notes into the beats as well as principle of superposition. Some of that, when a string is plucked, we get no particular frequencies. We don't get to pick which frequency it plays, but any ones that don't have that resonance, that don't fit onto that string, cancel out. So here, a lot of them disappear. These are ones that do fit a lot of the times. We get the resonant frequencies are here, the red waves. We get nice sort of peaks and troughs that stand. They present themselves, and they keep looking as if they're constantly there. Here, just recognize that antinodes are places where the object actually moves, whereas nodes are places where it does not move. We have the maximum constructive interference at antinodes, and nodes have a destructive interference at the nodes. Two things must be true whenever we talk about waves on a string. First, to get those standing resonant frequencies, each end of the string must be a node, and each harmonic that we talk about has to have half wavelengths, and that's going to be true for almost everything that we do. We've got to add half wavelengths every single time. So know the difference between the first, second, and third harmonic. Be able to get the wavelength if I give you the length of the string and which harmonic we're talking about. And then from there, if you know the speed of the wave, be able to get the frequency. And if you know the frequency, be able to get the speed of the wave. As we go up in harmonics, the wavelength gets shorter and the frequency gets greater by that same amount. We are not changing the speed of the wave if we just change the length of the string, or if we change harmonics. We're not changing that velocity, it remains constant. So here, now on the first harmonic, we have half of a wavelength. You see that we go from equilibrium to equilibrium, but in order to get a full wave, we would need to go to the next equilibrium. We have to go through a trough. Here on the second, we do one full wave if you'll follow one of those paths. So the length of the string is equal to the wavelength. And here on the third harmonic, we have three half wavelengths there. So a wavelength is 2/3 of the string. And again, wavelength, frequency are proportional. So if I now have a wavelength that is 1/3 of what it was, my frequency is 3 times what it was in order to keep that velocity the same. Here, my wavelength got cut in half, which means my frequency had to be doubled to balance that out. As you go up in harmonics, if you take the fundamental frequency and multiply it by the number of the harmonic, that gets you the frequency for that harmonic. And you can do the same thing with the wavelength as you go up, but divide it instead. If you know the wavelength of the fundamental, which you can find by knowing the length, and you divide it by the number of the harmonic, that is your new wavelength. Here's just more of that, a couple different looks. nodes, antinodes. Every time that you get a loop, that is half of a wavelength. One loop is half of a wavelength. So here we have half a wavelength, 2 half wavelengths, 3 half wavelengths, and on and on. The only way with strings that we can change the velocity is either by changing the tension or by changing the density of the string, making it a thicker or sort of heavier gauge string. So with that, just be aware that unless you're changing tension or the actual density, the actual type of string you're talking about, you're not changing the velocity. So for instance, if you've got a mechanical oscillator that is locked into a particular frequency, it says it always vibrates at this frequency, and you just lengthen the string, well then you've got the same frequency, and just lengthening the string doesn't change the velocity at all, so your wavelength has to be the same. Now you can add on loops, but you cannot change the actual wavelength. So here's a couple sample problems. I think those were mostly out of the homework, some of the homework problems. Again here, the frequency depends on the oscillator. The fundamental is 2 times the length of the string, and the velocity is dependent on those 2 things. If you need this equation, it will be given to you. You don't have to memorize it. A couple more sample problems. Check the homework for some of those. Let me see which worksheet deals most with strings. I believe it was worksheet 7 is a good one to look at. That first one on 7, as well as, I'm sorry, I guess that would be page 11 there. And then worksheet number 6, the front side. Worksheet number 6, the front side is going to be your best bet for working at strings. Doesn't look like I have the tubes on this one. Let me pull up a different file. All right, here we go. So we got 2 types of tubes, open-ended and closed-ended, and a lot of the same rules apply. We're going to start with the open-ended. Here, just realize that instead of ending on a node, you end on an antinode, but we still start with a first harmonic that is half of a wavelength, and all of the same rules apply here, just instead of starting on a node, we start on an antinode and end on an antinode. Be able to draw those, be able to work through some of those. And some of the problems we did with these in particular were where we talked about adjustable lengths, and kind of like I was mentioning with the string earlier, if we have a particular oscillator, a tuning fork, that frequency is locked in. If we're not changing the temperature of the air now, our velocity is locked in, which means that the wavelength is also locked in. And here's the thing, in order to get resonance, you have to add on to that first harmonic a length of tube that is equal to half of a wavelength. You always have to add enough space to fit a half wavelength in. That is true for strings, that is true for open-ended tubes, and that's also going to be true for closed-ended tubes as well. So be aware that if you can find your first resonance, sort of where that first harmonic fits, then to get further points of resonance, further points where you're going to get sound to resonate, you have to add on a half wavelength. Here with and here are sort of the weird ones, are the closed-ended tubes, one end closed, one end open. Here, instead of being either both open or both closed, one is closed. One is a node, one is an antinode. The node occurs at the point where it is closed off. Examples of these would be, capped boom whackers, the big sort of tubes that we hit earlier during the unit. Water in a tube, kind of like in the demonstration I had where I spilt water everywhere. That would be another example of a closed-ended tube. Clarinets are closed-ended tubes. But here, if we have a node at one end and an antinode at the other end, that is only a quarter of a wavelength. Our first harmonic is just 1/4 of a wavelength. This is where it sort of separates itself from the other. So now, same length of tube, but now our wavelength is 4 times the length of that tube. With a larger wavelength, that means a much lower frequency. So these have a lower frequency than the open-ended tubes. And then again, same rule applies. We can only add a half wavelength. We have to add on a whole loop when we go to the next harmonic and the next harmonic and the next harmonic. Or if we are keeping the same frequency and we are getting to our next resonance point, we have to add one loop. So we start with a quarter of a wavelength, and then we add a half a wavelength, which gives us 3/4 of a wavelength. And then we get, down here we get 5/4 of a wavelength and 7/4 of a wavelength, fitting into that length of tube as we go up in the fundamentals. And notice that these different harmonics, we alternate. We skip the even numbers. We go from first to third to fifth to seventh. That's because this has 3 times the amount of wavelength as the first one. So if we start with a quarter here, this has 3 times, which means as the third harmonic. This one has 5 times what the first one had, so it's the 5th harmonic. And again, kind of like we did with the other ones, we calculated if we held a tuning fork here and we wanted to extend the tube longer and shorter, at what lengths would we be able to get that resonance at, be able to get that, that length of resonance, be able to just calculate what the wavelength is for those tubes and strings, be able to calculate frequencies from that, be able to draw those as well. And much past that, I think, let me go back to here for beats and superposition, then we'll call it good. So superposition, the idea here is that if you have 2 crests, so if you notice both of these waves are up, I guess you could call them, as they sort of layer on top of each other as they go, they constructively interfere. So this wave here in the middle, and that's not gonna let me break off. But if we were to have those 2 waves combined, because they're the same width and amplitude, in the middle here, it's going to be twice as high as it was to start with. But this is the shape we get. Because they are both sort of up, they add to each other. Whenever you're trying to draw these, I would just recommend, this is a relatively solid piece. So maybe make that your bottom. And this kind of just gets plunked on top. If you look, as they cross over, we have to add the amplitude at each point along this to the other one. On the other side, I'll put them in the wrong spot, but it's all right. On the other hand, we also have destructive interference ones. So here is an example where if they get to the middle and they overlap, if you just sort of put them in the middle, that is the case. But what this is saying is that this bottom piece has to be taken out of the top piece. So the shape we'll actually end up with would be this. Draw a line in there and draw a line there. So because they destructively interfere, we start with this sort of positive piece, but then that shape that was on the bottom has to be taken out of it. So we took sort of a circular side, a semicircular shaped chunk out of that square. So this is the shape that we end up with. And last but not least, our beats. Whenever you hear 2 sound waves of similar frequency together, you get this phenomenon known as beats. The beat frequency is the difference in the frequencies of the 2 sounds. And you can use that beat frequency. 1 over the beat frequency gets you the beat period, the time it takes between beats. And again, these have to be relatively close together. We're talking about 10 or 20 hertz difference, maybe 30 hertz. But when we start getting up too high, the beat frequency becomes large enough that we cannot hear it. The beat period becomes very small and we can't perceive that. So you get this sort of going in and out of sound. You start getting constructive interference here in the middle, but destructive interference out here where you get these sort of loud and then soft and then loud and then soft sounds. Again, beat frequency is the rate at which sounds get louder and quieter. The beat period is reciprocal of that. If we've got these 2 waves, they go in and out of phase. When they are in phase, that is when they're constructive, and you get this nice big piece here. And then when they are out of phase, they are destructive. You get a pinch, and you get a much softer sound there. Answer to A, how long does each beat last? Well, really you need the answer to B first. How many beats would you hear per second? That is just the frequency, so 155 minus 150, that gets you 5 hertz. And then how long does each beat last? That is the period, which is the reciprocal of 5, so 1/5 or 0.2 seconds each beat lasts. The beat frequency is only dependent on the difference. It doesn't matter what the absolute values are. So the beat frequency is 6 here for the top one, and it's 6 here for the bottom one. Just because the frequencies are different doesn't mean that the beat frequencies will be different. That is only dependent on the difference between the frequencies. Two frequencies have different amplitudes. You need to be able to identify if that is the case or not. And the way to do that is to look at the graph and say, all right, in this top one, we have a very pinched middle. That middle between those two sort of beats is pinched off entirely to 0, whereas down here, it does not pinch off. If it does pinch off, that means you get complete destructive interference. The sound waves cancel each other as completely as possible. That means that their amplitudes were the same, right? If you've got 4 and then the other wave is 4 as well, if they destructively interfere, you get 0 as that sort of middle amplitude where they are destructing as much as possible. But here, let's say we had 6. An amplitude of 6 for one wave and an amplitude of 2 for the other wave. Well, the most we can get is 8. When they perfectly constructively interfere, you get an amplitude of 8 on those waves. They add together. But here, the least we can get is 4. If you have $6 and you make a $2 transaction, you either end up with $8 or $4. You either gained or lost those $2. So we still have an amplitude here in the middle. At the lowest point, we still have a wave that is present. So that is the difference, be able to recognize if you have a graph. Are the amplitudes the same or are they different? And are the frequencies the same or are they different? And that is all I've got for you. Hopefully that is helpful in guiding you. Remember, as always, this video is not enough to get you through the test. Definitely look at some of the homework packets. Again, number 6 for strings, but worksheet 8 is sort of the whirlwind tour of everything. It's got a little bit of everything on there. Some of the other ones, just to make sure you're solidified up with those earlier ideas. And then definitely the test practice problems, which we'll have some time in class to work on as well. Hopefully this was helpful, and enjoy your studies.